In my series on structural engineering made simple, today I talk about design of single footings. Please take a moment and read the disclaimer at the bottom of this page before we continue. Foundations in the form of single or double footings, continuous or spread, play the role of transferring forces from columns to the soil. They must be able to withstand forces applied on them from the columns, and at the same time, they should provide a firm pressure on the soil so that the applied pressure may not exceed the bearing capacity of the soil. Therefore, when designing them, we must look into foundation stability and the limit on the soil bearing capacity to withstand the applied pressure. The contact area with the soil is a determinant factor in this case. Proper design of the foundation to make sure the size, the contact area, is acceptable and the foundation has an adequate amount of steel for bending and appropriate thickness for shear. Potential for settlement that can occur in a short and long duration loading. This lecture provides an overview of different types of foundations. An example problem explaining the design of a single footing, which is sometimes called an isolated foundation, is presented. This video is the 16th lecture in my series on structural engineering made simple. Please note that the materials presented for checking the shear and design of bending reinforcement require prior knowledge on general reinforced concrete shear and bending design in beams. Therefore, I recommend watching my lecture number 7, 8, and 9 of my YouTube series on structural engineering made simple. These are the pertinent references used in the preparation of this video. Bearing capacity. This is an allowable pressure with factor of safety included, specified for the site. This value is obtained as a result of geotechnical investigations. It mainly depends on the type of soil. You will need to hire the services of a geotechnical engineering laboratory to conduct site investigations, obtain samples, and test them and provide you with a report. For example, if the soil lab report indicates an allowable soil bearing capacity as 3000 psf, it means the soil pressure exerted from the foundation to the soil beneath it cannot exceed 3000 pounds per square foot. Some soil lab reports provide the ultimate bearing capacity. In that case, make sure you divide the value by a factor of safety, which is around 2 to 4 to get the allowable soil bearing capacity. Different types of foundations. Depending on the column load and type of soil, the foundation may consist of isolated single footings, twin foundations, continuous foundations, mat foundations. If the soil bearing capacity and the column loads do not allow any of these types, then foundations with piles or caissons are considered. In a single footing, in general, there are two moments and one axial load transferred from the column to the footing, as shown in here. A pedestal is used for steel or timber columns to protect them from the contact soil. As you can see, in this case, a concrete pedestal is used because the column is a steel column on base plate. A question is the column to footing connection fixed or hinged? A fixed support means that all the three forces are present and transferred from the column to the footing. A hinge support means that only the axial load is transferred to the footing. Whether we can consider the connection fixed or hinge depends on many factors. Concrete columns are generally always considered having a fixed connection. Steel columns with base plates and many anchor bolts that are properly designed are considered fixed. Steel columns with base plates and only two anchor bolts are generally considered hinged. Let's examine the following details of a steel column attachment to the footing. In this one, as you can see, there are many anchor bolts are used. These are the anchor bolts. In this situation, anchors work with shear and tension and provide the resistance needed for moment transfer. Therefore, the connection is fixed. In contrast, in this one, as you can see, only two anchor bolts are used. One is in here, the other was in the back. In this situation, anchors work with shear only. Therefore, the connection is hinged. Details of a single footing for a steel and a concrete column are shown in here. The figure to the left shown is a concrete column attached to the foundation. The upper portion is a plan, the lower portion is a cross section. You notice that in this case, the column is directly attached to the foundation. The one to the right, the column is a steel, and you notice that the concrete pedestal is used. The reason for that is that we don't want the steel to come in contact with soil, otherwise it would corrode. Also note that in a single footing, if there are no concrete ties connecting footings together, there is a possibility for a slight rotation of the footing. In this case, regardless of whether the column is concrete or steel, the slight rotation, which may be only a few degrees or less, will cause the connection to behave like a hinge. Let's examine this in a figure. What do we mean by concrete ties? As you can see in this figure, the isolated footing, in this case, has two additional members. These are concrete elements attaching one footing to the other. Therefore, the possibility for the rotation of the foundation is almost zero. And as a result, we can consider the attachment of the column to the foundation to be a fixed one, as shown in here. In contrast, in this figure, you notice that there are no concrete ties used. There is a possibility that the foundation may rotate. And as a result, the connection may be considered as a hinge. Again, the rotation could be only a few degrees. Twin or combined foundations are used when the land boundary will limit the extension of the footings for external columns. If external footings are used as isolated ones, they will be severely eccentric. Here are some details. The figure to the left shows a standard twin foundations. You notice that the boundary with neighbor's land is too close to the foundation. Therefore, we are attaching these two together using this what we call twin foundation. The figure at the bottom shows the cross section. The one to the right, as you can see in here, to save concrete we have used a trapezoidal detail. However, in the cross section it would look identical to the one to the left. A continuous foundation is a beam-like footing supporting multiple columns in a row. Here is a detail. You notice that in this case, in the plan, as you can see in here, we have attached all these columns together through a one beam-like foundation. And at the cross section, you notice the location of the columns and each one is uh, supported by this continuous footing. An example of a spread foundation is shown in here. In this case is a slab used to provide the support for the columns, and here are the columns. This is one of them. And if a solid flat slab is used for the footing, there should be precaution to avoid water pressure built up from below the foundation. Otherwise, a buoyancy situation may occur, compromising the foundation stability. Thus, proper water drainage must be maintained. In some applications, the slab is accompanied by certain types of beam-like footings that are running in between the columns. Foundations on piles. Piles are column-like elements driven into the ground to transfer load from the column to the ground. Piles resist by the reaction of a bearing resistance Rb and a skin friction resistance Rs. If a firm or solid bed is not reached, then the resistance can only be through the skin friction resistance. The force transfer to each pile is simply obtained using the action of the axial load of the column and bending moments. I will demonstrate this in the next slide. The simple case of a 4-pile foundation is shown next. Here is a simple case of a 4-pile foundations. In the figure at the upper left, you will see the plan of a single footing which is resting on 4 piles. So this is one of the piles and there are 4 of them, and here is the column. The distance of each pile from the center of the footing is C. In the lower figure, you will see the cross section. Here is the foundation and the piles. The piles could be steel, timber, or concrete. Now the distribution of the forces to the piles are obtained from the famous equation of PA plus or minus MC over I. However, here, rather than the area and the moment of inertia, we simply use the number of piles. For example, for the area, we just have 4 because there are 4 piles. For the moment of inertia, we simply take the distance to the power of 2. And we can show that this would convert into a simple equation of P over 4 plus M over 4C, and that's the maximum force. And as you can see, when the bending moment is acting like this, then the piles to the right would be subject to this, and the piles to the left would have the negative sign. P sub P, therefore, is the maximum force in a pile. P, which is over here, is the axial load from the column, and M is a bending moment from the column. In this figure in here, it shows the force applied on the pile being resisted by a bearing resistance Rb and the skin friction Rs, as we discussed in the previous slide. Foundations and caissons. Caissons are like piles, except that they are larger in their diameters and cast and embedded differently. They mainly work with bearing rather than the skin friction. Design of caissons depends on the type of soil and different layers of soils at different levels. Depending on the type of application, caissons may be the box type or open, in other words, without bottoms. Some are pressurized, especially when underwater work is involved. Here is an example of a caisson. This is an open caisson. In this type, the jacket is made of several pieces that we call them rings. So here is one of the rings. This is one of the rings. And that is the load from the column. The first ring is installed, upper one. the soil is dug out and a second ring installed, which would help lower the first one. Again, the soil is dug out. The process continues until the desired depth is reached. The caisson is then filled with concrete to provide a solid foundation. Here is filled with concrete, and you will see down in here the bearing resistance. Requirements for footing sizing and design. Design of footings in general involves three different analyses. Analysis of foundation stability, analysis of the foundation to determine its size, in other words, the footprint, and checking for the soil pressure, and computation of the footing settlement because of soil consolidation. And analysis of foundation for flexure and shear and design for reinforcement. The first two analyses are often related and can be done together. These analyses, the first two, require service loads. In other words, no load factors are used in the column axial load and bending moments. However, a factor of safety must be incorporated in the soil bearing capacity. Bending and shear and design for reinforcement require factored forces and are conducted just like beam or slab design. Let's concentrate on single footing design. Perhaps a good method for a single footing design is deciding on the size of the footing and its thickness first, and then doing the three aforementioned analyses to determine whether the footing design is satisfactory. When deciding on the size and thickness, remember that the bottom of the footing must be deep enough to avoid the frost line in cold regions and to reach good quality soil. So we are talking about at least 3.5 feet below the surface. Often the top layers of soil are called topsoil, which has no structural values. The following illustration shows the dimensions of a footing. Please note that in the direction the bending moment is applied, the footing effective length is B, here it is, while its width in the perpendicular direction is A. CA and CB are the size of the column or the pedestal. Therefore, the contact area is A times B. The moment of inertia of the footprint is AB cubed divided by 12. Furthermore, we compute the weight of the soil PS. We're talking about the weight of the soil in here. And weight of concrete, we call it PC, which is the weight of the footing. PS is gamma S times area times HS. PC is gamma C times area times H. Gamma S and gamma C are the soil and concrete densities using the unit of pounds per cubic foot. HS is the height of the soil over the footing, we call it overburden, and H is the footing thickness. A typical value for gamma S is around 90 pounds per cubic foot and gamma C is about 150 pounds per cubic foot. We are using an approximate sign in here because when you look at the detail to the right, there is a portion in here that there is no soil. It's actually concrete. However, approximately we assume everything is made of soil for simplifications. Also notice that when we apply the load as shown in here, the bending moment, this is called the toe and this is called the heel. With the applied load from the column being P and the moment M, the total load is P plus PS plus PC. And we can consider an eccentricity as moment divided by PT. I'm going to show this eccentricity in the next slide. So here you will see the eccentricity. If the total load is PT, we are putting the load PT as a distance E. E is the eccentricity, which is m divided by PT. The pressure from the footing on soil, at the toe we call it PT, and at the heel we call it pH. And they can be computed, the famous equation P over A plus or minus MC over I. So the equation is written here. I substitute for the area and the moment of inertia, and at the end for the toe pressure I come up with this equation. For the heel pressure is the same equation, except there is a negative sign in here. Notice that there is a possibility for the heel pressure to become negative. Why? That happens when 1 minus 6e over b becomes smaller than 0. If a negative pressure happens, then an uplift will happen. To avoid the uplift, therefore 1 minus 6e over b must be positive. In other words, 1 minus 6e over b has to be larger than 0. Using that equation, we notice that the eccentricity therefore must be smaller than b over 6. So if the eccentricity is smaller than b over 6, we will have no uplift. If we divide b into 3 segments, and the resultant force PT acts within the middle third of b, no uplift will take place. In general, if there is no restriction to increase the size of the footing, we can increase b and come up with a footing size in which E is always smaller than b over 6. However, if the size cannot be increased and the negative pressure occurs, we must ignore the negative pressure and recompute the pressure. This is because once an uplift occurs, there is a partial loss of contact between the footing and the soil. Let me demonstrate this for you. In fact, by maintaining the equilibrium of forces, we will be able to recompute the pressure. So here it is demonstrated. You notice that after we computed the heel pressure and toe pressure, you can see the figure to the left, we will have some negative pressure happening over this area. This is where the uplift would take place. However, once the uplift would take place, there is a loss of contact. So we need to recompute the pressure. And in that case, the new contact is B prime, the new pressure is P prime sub T, and distribution is a triangle. So we need to find this distance P prime and the new pressure P prime T. The resultant force for the pressure on the soil, let's say it is equal to R. The force acts at a distance equal to B prime over T from the toe. R is the resultant of this triangular force, which is acting at a distance 1/3 from that point or 2/3 from that point. Therefore, by knowing that and lining up the force capital PT with R, we are able to find an equation for P prime T and an equation for B prime. Here are the equations. B prime over T is equal to B over T minus E from the previous figure, and from there we come up with a new contact area, which is represented by B prime, is 3 times B over 2 minus E. And by writing the equation for R and knowing that R is equal to PT, we come up with the new equation for the toe pressure, which is P prime sub T. In any case, the maximum pressure applied on the soil cannot exceed the allowable soil bearing capacity. If PT in the case of the full contact or P prime T in the case of partial contact exceed the allowable soil bearing capacity, then the size of the footing must be increased to bring the situation under control. Design for bending moment. In this type of analysis, the axial and bending moment from the column must be recalculated to include the load factors. We must recalculate the pressure on the soil with factored values of the axial load and bending moments. However, we do not have to add the weight of the soil or concrete to the axial load. Why? This is because the soil pressure from these weights are balanced with the applied force from the weight of the soil and concrete. Thus, the weight of the concrete and soil do not cause any flexure or shear effect in the foundation. Here we'll see calculations again. The toe and the heel pressures are recomputed using the factored loads. Again, if uplift occurs, we must recompute the partial contact area and the correct pressure on the soil. The new eccentricity, we call it E prime, which is mu divided by pu. Well, what is mu and what is pu? Mu is a factored mu is a factored applied moment, pu is a factored axial load. As you can see, it's very similar figure, except that the load is pu, the toe pressure is p sub tu, and the heel pressure is p sub hu. If we have partial contact, then we have to recompute p prime tu using a similar equation as I gave it to you before. The design of flexure is similar to that of a cantilever beam. In a way, if you look at this illustration, you notice that because of this pressure, which is trapezoidal, the footing is bent upward. Therefore, we need to design reinforcement at the bottom, like this. And in the perpendicular direction, of course, we would put the same amount of reinforcement because we always design this for the maximum bending moment. If the bending in the other direction is smaller, we can use the same reinforcement conservatively. Now, how do we find these pressures? You already noticed that if the distribution is trapezoidal, we have the toe pressure and we also have the heel pressure. So from the geometry, by knowing this distance L, we can simply find this P2U. The design moment is called MUF. Please don't make a mistake between this MUF and the MU which is applied. This MUF is a bending moment that happens at this location X. That's the critical location for the bending moment of the footing. The length of this cantilever is B minus C sub B, the product divided by 2. Remember, C sub B is the size of the column. The location of this moment is at the face of the column or the pedestal, as you can see down in here shown with X. Again, P1U is the maximum soil pressure at the toe. P2U is the soil pressure at the critical bending location X. PTU is computed by knowing that the distribution of soil pressure is triangular. All calculations, by the way, are done for 12 inches of the width of the footing. In other words, in the perpendicular direction, we consider 12 inches, similar to slab design. So let's compute MUF. By knowing that trapezoidal distribution, we can show that MUF is equal to this value. The design for reinforcement is now done just like the rectangular section singly reinforced beams or a one-way slab. It's more closer to design of a beam, as you will see. However, the fact that we use 12 inches of the width is similar to slab design. And if you are not familiar with reinforcement design for slabs and for beams, please see lessons 7 and 9 in my YouTube series on structural engineering made simple. While watching those lessons, notice that the width B is equal to 12 inches like one-way slab design. The effective depth H the effective depth D is determined based on the protection cover 3 inches in this case and bar diameter. So if we have the thickness of this slab, which is H, we can compute D. And like the slab design, it is a good idea to select the bar size first and the footing thickness, and then determine the area of steel AS that is needed. And I'll show you the steps in computing AS. But before we do that, first let's see what is D. D is equal to H minus 3, and I recommend using 1.5 times the diameter of the bar. dB is the diameter of the bar. Why? I'm going to demonstrate it to you in my next slide, and why I'm using 1.5 times the diameter of the bar. So please notice that the unit for MUF is inch kips or foot kips per foot. Therefore, any steel that we design would be per foot of the footing width. All ACI requirements on the steel design will govern this case. Also note that the steel will be at the bottom as we mentioned before. And here I show you a typical detail of reinforcement for the foundation. This figure at the top shows the plan, which is like a grid. This figure at the bottom shows the cross section. There is a grade in there, the main bars. And now you realize that why I insist of using D equal to H minus 3 inches plus 1.5 times the diameter of the bar. As you can see in here, the bars are like a grade. Therefore, it's a good idea to use the distance with respect to the center of the first layer of bars, just conservatively. For shear design, usually no stirrups are used. The footing thickness can be designed to adequately take care of the shear. However, the shear is done for two different conditions. These are called the one-way and two-way shear actions. For most typical cases, the critical shear location for one-way action is at the distance D from the face of the column or the pedestal. The critical location for a two-way shear is at D over 2 from the face of the column or pedestal. The shear resistances are, for one way is phi V sub C equal to phi 2 square root of prime sub C BD. And for two-way, as I said, for most typical cases, is 4 times the square root of prime sub C B sub T times D. I tell you what B sub T is. And remember, B is 12 inches. Phi is the resistance reduction factor. So in these equations, a prime sub C is a compressive straightening of concrete. Phi is a resistance reduction factor for shear is 0.75. B is equal to 12 inches. Now, so what is B sub T? This is the perimeter of the area at the critical location. So critical location is D over 2. So you are talking about what we call the punching area. In other words, if I show you the footing, which looks like this, and pedestal or column, we go at the distance D over 2 from each side, and then we have this area, which is the punching area. So perimeter of this area is equal to this value, and that's B sub T. The applied shear VU needs to be less than phi V sub C for the design to be satisfactory. How do we find those? For one-way shear action, it is simply P1U plus P3U. I tell you what this one is, times L minus D over 2. And for two-way is P1U plus P4U, A times B minus that puncture area, divided by 2. By the way, the unit for shear, for one-way shear, is pounds per foot or kips per foot. However, for two-way shear, the unit is just pounds or kips. So let's examine these equations in the figures for clarification. So now we know what is that P3U. Again, once you have that trapezoidal or triangular distribution, find from geometry the pressure here, right, at the critical location for one way, and that is the applied shear. The average of these two, P1U plus P3U divided by 2 times L minus D. A very small amount of shear. In the perpendicular direction, we're just using 1 foot or 12 inches. In this one, I show you now the puncture area, which is here, the over 2 from one side, the over 2 from this side, and average pressure is P1U plus P4U divided by 2 multiplied by the puncture area deducted from the total area. Remember, this is B sub T in this case. All right, so I'll keep this for a few seconds. You look at it. And there are a few observations that I want you to pay attention. The equation for 5VU for two-way shear action may change if the dimensions A and B are not the same and very different from one another. Please see ACI 2014 or the later edition for proper values for adjustment of the shear resistance. If A and B are very different from one another, ACI has rules for distributing flexural steel with more steel around where the column is. Again, see the ACI 2014. So you put more concentration of steel closer to where the column is. As you go away from that, it would spread out. If the applied moment from the column in a biaxial moment case in the perpendicular direction is significant, make sure to add the pressure from the moment to the maximum toe pressure and check it against the soil bearing capacity to make sure the footing is stable. In other words, you get a little bit of pressure from the other direction as well that you added to the toe pressure. In situation with uplift, if the uplift extends more than about 25 to 30% of the size of the footing, it's a good idea to extend the footing width. If that is not possible, consider using tension anchors to hold the footing down. Twin foundations may be another solution. So again, if this is the footing and we have, this is a column, and we have a severe uplift happening, let's say in here, then we can use some tension anchor that have a big dead weight attached to them and to prevent the uplift from happening. But again, this is only if you cannot extend the footing and fix the problem. Let's look at example. Here we have a single footing again with the moment M and axial load P, and we want to provide the support for a 20-inch by 20-inch concrete column. Bottom of the footing is at a depth of 4 feet. And we have the total axial load as 50 for dead load, 33 for live load. For the moment, we have 35 foot cubes for the dead load and 19 foot cubes for the live load. We have selected the material types of prime sub C as 4000 psi and F5, which is a steel bar, yield strength at 40,000 psi. The allowable soil bearing capacity in this case is given by the problem as 4000 psf, pounds per square foot. Soil density 90 pounds per cubic foot. And we're going to try a 6.5 by 6.5 foot footing with a thickness of 18 inches. Now, if you find out that 18 inches is too much, we can reduce it, but usually we are a little bit more conservative in thickness. We don't go for a very, very thin slabs for footing. So I would say probably 18 inches, maybe we can go down to 16, but certainly we don't want to be very thin slab used. Therefore, in this case, A is equal to B is equal to 6.5 feet. Size of the column is 20 inches. CA is equal to CB is 20 inches. HS, remember HS was the height of the soil, is 4 feet minus thickness of the footing, so it's 2.5. Thickness of the footing, which is H 1.5 feet. So with that, we can compute the total load. We add we don't use any load factors in this case. So totally we get the 56 for dead load, 33 for live load. We get 89 kips, and therefore when we compute this weight of the soil, the density times the area, and this is in pounds, so I divide it by 1,000, I get kips, and I get the weight of the concrete, which happens in this case also becomes 9.5. 150 is the density of concrete, multiplied by the size, multiplied by the thickness. Adding those together, we get 108 kips. Adding the moments together, we get 54 foot kips. Therefore, the eccentricity is equal to, if I find it in inches, is 6 inches, which is half a feet. And certainly it is less than B over 6, so there is no uplift. That means the distribution is trapezoidal, as shown in here. So we compute PT, which is a maximum one, using our equation. We end up with 3,730 pounds per square foot, less than 4,000, so our footing is okay. And now we want to design reinforcement. So I'm showing the figure again with all the 4 values of P1, P2, P3, P4 shown, but I put a little U in here because these are based on factored values. So PU is 1.2 times 56. These are the load factors, and 1.6 for the live load. And the MU is the factored moment. The new eccentricity is 0.6 feet, but it still is less than B over 6, so we have no uplift. And these are the extreme pressures, the maximum with the plus sign, the minimum with the negative sign. One is in the heel, the other at the toe. Now, by knowing the geometry, knowing that L is equal to this value, we know the D, etc., we can find all the other values. So notice that here I start by using a number 4, and I suggest that you select the bar size first. It has a diameter of 0.5 inches, area of 0.2 square inches. So with that, I come up with the D, and that's how this D 1.19 was computed. And L, therefore, is 2.42. All right. From there, you simply find the P2U just from the geometry and P3U as well. So you get 3.24 for P2U, 3.824 for P3U. So you have all these little pressures computed now. So you're ready to go ahead and use them in your equation. So using it in the MUF equation, you get 11.77 foot kips. And following the procedure in lesson 7 of my lecture series on structural engineering made simple, we have to divide this by a capacity reduction factor or resistance reduction factor. We call it MN. And for flexure, we assume 0.9, and then we have to check it later. So it's 13.08. This is how much bending capacity I need. Then there is another factor called R, which is this Mn divided by BD squared, and make sure to be consistent, pounds and inches. That's what we use in concrete design. So B, we use steel 12 in the perpendicular direction, and this is a D that we found. And the value is has nothing to do with the stress. It's just the value is equal to PSI. I mean, the unit is PSI. We also need to find this parameter M, which is a material factor, is a steel resistance or yield capacity divided by 85% of concrete compressive strength is 11.76. And the equation for a steel ratio is this equation. If you have not seen it, please see that lecture number 7. Plug numbers in there, make sure to make the units consistent, you get the steel ratio rho. And this is, of course, smaller than the minimum. Minimum steel ratio is 200 over Fi. You notice that this is smaller. So we can use either the minimum, but a lot of times the ACI code allows 4/3 of the required steel. Let me show you what it means. Required steel is 0.0163, this is steel ratio, times 12 times D, multiply by 4/3, so I get 0.37 square inches per foot of reinforcement I need. And that in order to find out what is the spacing, you always multiply by 12 inches by the cross-sectional area of the bar divided by how much steel you need. So you have to put these bars at 6.5 inches apart. So you might say, I want to know how many total bars I need to use. That's simple. You have 6.5 feet, multiply by 12, deduct 3 inches from each side because you have to have protection cover, and then whatever the value is divided by this spacing of 6.5, that gives you the number of spacing. Let's say the number of spacing is 11, that means the number of bars would be 12. So actually in this case you have 12 number 4 bars put in the direction that we just designed, and you repeat the same number of bars in the perpendicular direction. Please notice that I mentioned we need to recheck this phi value, but because we are using a steel which is smaller than minimum amount, is guaranteed that the capacity is equal to capacity reduction factor is 0.9. But if you want to know how this one could be checked, please take a look at lecture 7 as I told you about. All right, let's look at one-way shear. That's the total applied shear using my equation. I come up with 3.8 kips per foot. Remember, for one way is kips per foot. And the resistance 5 is sub C, 0.75 resistance reduction factor, 2 times the square root of 4,000 times 12 times 14.25. In one of my presentation slides, and I had concrete design, one of the viewers asked a question and said, I don't see the units working out in equations like that. Now, if you're familiar with ACI, ACI's official units are inch and pounds, so it doesn't matter. There's always a square root of prime sub C appears. You put PSI in here, you get pounds out. So the value, you have pounds, because the calculations are done per foot, is per foot, or is 16.2 per kips. These equations are empirical equations, and they do not work out if you want to do the units on those. A lot of our viewers who are outside of the United States, who are not familiar with the ACI code, often ask me these questions. So again, you always use pounds and inches. PSI for a prime sub C, you get pounds and inches out. In a lot of equations, ACI have this square root of prime sub C. For two-way, now we need to compute that B sub T, which I gave you the equation before. And that's simply computed because we have all the sizes. Make sure not to mix up the units. So you notice that I have divided the area that was in computed over here in terms of inches, because here I have feet, here I have inches. I divided by 144, which is 12 to the power of 2, to have everything now computed properly. And the unit for this one is kips or pounds. 1 kip is equal to 1,000 pounds. Again, for our foreign viewers who are outside of the United States. Okay. And the resistance for two-way, in this case A and B are the same, is this equation. I plug numbers in there. I know B sub T, 137. And I come up with applying the reduction factor, I come up with 370.4 kips. So it's okay. It's much larger than the applied. Okay for one way. And our design is therefore okay. Please note that in the foregoing computations, we did not consider the potential for the foundation settlement due to, for example, consolidation of the soil. For that type of analysis and finding out whether it may become critical in your design, please hire services of a geotechnical engineer. Thank you for watching this video.